Thank you very much. I should thank the organizers for their kindness to invite me. This is my second time in Beirut. The first time I was here was in 2017. So thank you very much. It's an honor. And I just want to make a short announcement before I start. Namely, the notes, they are handwritten notes. I have prepared notes for these lectures. So at the end of the week, I will give the notes to Florian, and I assume you'll be able to distribute it to everyone. In addition, later today, I will email Florian copies of papers that are closely related to what I'm going to do this week. Okay? And you'll also get copies of those papers. They are all published papers. Okay, so as you know, the Fourier transform characterizes smoothness of a function, and this is captured by the Paley-Wiener theorem, which says, so this is a usual Fourier transform, so here is how I write the Fourier transform. Oops. So here, I should say what U is. We'll take U to be, say, for example, a continuous function of compact support in Rm. And then the Fourier transform is defined by this integral because it is of Fourier, because it is of compact support. The integral makes sense. And the Paley-Wiener theorem says that the function U is C infinity. If and only if the Fourier transform decays rapidly. I write that like this, C minus k for all k positive integers. Okay, so it's very nice because you see this is a quantitative description. Okay, there is no differentiation involved here. Okay, and this characterization is very useful both in PDEs and complex analysis and other applications, applied mathematics and so on. Often, when you look at the regularity, the smoothness of a solution, U of a solution of a partial differential equation, then the Fourier transform is a very powerful tool for studying smoothness. The Fourier transform can also be used to study Gevrey regularity. Okay, so I'll talk about this in the coming days. And then there is the question of real analyticity. So I will denote by C omega real analyticity, the space of real analytic functions. So if it's on an open set omega, on an open set, say, capital omega, these are the real analytic functions. The Fourier transform can be used to describe real analyticity, but one Fourier transform is not enough. Let me give you a reference. You look at the book by Hormander, volume 1, the analysis of linear differential operators. There is a chapter where he talks about how the Fourier transform characterizes real analyticity. And the thing is, he has to take a sequence of functions of compact support whose derivatives up to a certain order are controlled in a certain fashion. And so you have to look at the Fourier transforms of a sequence of them in order to decide, in order to say whether the function U is real analytic or not. And that is not convenient in applications to partial differential equations. Okay, and so the nonlinear Fourier transforms I'm going to talk about have the advantage that with a single transform, you can characterize analyticity. They also have the advantage that the same transform can be used to characterize the smoothness and Gevrey regularity. Okay, so so before I come to that, let me go back to the Paley-Wiener theorem. You see, one of the nice things about this characterization is that you can localize it. Meaning, see if I take a point x naught in Rm, and you want to check whether a function u is smooth near x naught or not. Any function u, any continuous function, say, it doesn't have to be of compact support. If you want to check smoothness near x naught, well, smoothness near x naught is a local phenomenon, and therefore I can take a smooth function phi, so that phi of x naught is not 0 and phi of compact support. I look at this. So u is smooth at x naught or near x naught, if and only if this is smooth near x naught, and then I can look at the Fourier transform of this. Okay. Okay. Now, so real analyticity. So here is the definition of what's called the FBI transform. The FBI transform, where f is well, Fourier has to be there. B and I, they stand for two physicists, actually. These are people who are studying quantum mechanics that introduced this transform, this nonlinear transform. Iagolnitzer. Okay, and it goes as follows. So I take a function of compact support in Rm. Actually, you can also be a distribution of compact support, but I'm going to focus on functions. Okay. So when u is a distribution, you are supposed to understand this in the duality sense, that u is acting on this smooth function. Okay. But in any case, let u be a continuous function of compact support. Then the FBI transform is a function of two variables, x and c. And it's defined by this integral, ei x minus y, inner product c minus norm of c, norm of x minus y squared, u of y dy. So u is of compact support, so this integral makes sense. So this is the dot product. So z dot c means some zj cj. And you know what this means. Now here x and c are in Rm. So this is, you see, so if I had only this part, it would be like the Fourier transform. But there is this nonlinear part. So that's why it's called a nonlinear transform. This is the nonlinear part. It's a quadratic part. Later in the coming days, I'll talk about even more further generalizations. But today, I'll focus on this one. And so, so this, it turns out, characterizes analyticity, real analyticity. Okay, so that's the theorem I'm going to prove today. But before that, so this is the FBI of u. So the first question that arises is, if I know this integral, can I recover u from this? So in the usual Fourier transform case, you have the Fourier inversion formula. You can write u in terms of its Fourier transform. Right? So here also, that's possible. There is an inversion formula. So that will be the first theorem. So by the way, I'm going to number my theorems. Okay, theorem 1, theorem 2, and then if there is a lemma 3, and so on. Okay, that will make it easier to make to refer to a particular theorem. So this is inversion of the FBI. And so, so I take u, a continuous function of compact support. And then u of x equals, for any x, the limit as epsilon goes to 0. If there is a constant to the power of m over 2, and then there is a double integral ct f of tc e to the power of I x minus t dot c minus epsilon norm of c squared, norm of c to the power of m over 2 dt dc. Now, let me compare it with the inversion formula for the Fourier transform. This term, it's there to make the integral convergent, okay? So this is there to make the integral convergent. Now, if you didn't have this term, this basically will be like the usual Fourier transform inversion formula, okay? Except you have a double integral here. You see, notice that here, you see the difference between this and this is just a function of one variable, c. This is a function of two variables, x and c. Okay, this is nonlinear Fourier transform. Okay, so, but otherwise, this basically looks like the usual Fourier transform inversion formula, and that's how it's proved, basically. So let me show you. The proof is quite short. So first, you have the integral ei x minus y dot c minus epsilon norm of c squared. This is an integral in the c variable. This integral equals pi over epsilon to the power of m over 2 e to the power of minus x minus y squared over 4 epsilon. This is this basically is because you see, what is this integral? This integral is basically the Fourier transform of this Gaussian function, okay? So put epsilon equal to 1. And for x minus 1, y put t, the variable t. Then eit dot c minus norm of c squared. You are looking at the Fourier transform of the Gaussian evaluated at t. And the Fourier transform of the Gaussian is basically itself, okay? So that's what this is saying. Okay? So this is the Fourier transform of the Gaussian. The Fourier transform of the Gaussian. Okay, so that's what I start with. Now I multiply by u of y and integrate in y. Okay, so this was an integration in c, so let's see, and then in y, x minus y dot c minus norm of c squared u of y dc dy. So I multiply this by y also. So the integral for epsilon u of y dy. So y integration, and then there are some constants. So 1 over 2 pi to the m. And here the constant becomes 1 over 2 to the m pi times epsilon to the power of m over 2. And now in here, I can change variables. I put t equal to x minus y over 2 square root of epsilon. Okay? And then when you change variable, see dy will be this number to the power of m over 2 times dt. So that will cancel this power of epsilon, the change of variables. And you get 1 over pi to the m over 2, the integral e to the minus norm of t squared. So the epsilon 2 times square root of epsilon times t dt. Okay? And now if you let epsilon go to 0, remember u is continuous of compact support. If you let epsilon go to 0, this uniformly will go to u of x times whatever the integral is. Well, you know what the integral of the Gaussian is. It's this number. And so this goes uniformly as epsilon goes to 0 to u of x uniformly on all of Rn, I'm saying. Uniformly on Rn, okay? And that therefore this goes to u of x. Okay, so how am I going to get the FBI in there? Well, that's going to be easy. So if you have any questions, please stop me, okay? Raise your hand, so just stop me. And so u of x, which, as I just showed, is the limit of this as epsilon goes to 0. Goes to 0. So I have this constant. Integral e I x minus y dot c minus epsilon norm of c squared u of y dc dy. Okay, so I have c integration, y integration. And, well, this is the FBI transform. And so to get the FBI transform in there, what I do is, okay, so this is, so you have some constant 1 over 4 pi cubed to the m over 2 limit as epsilon goes to 0. Of now I'm going to get a triple integral e I x minus y dot c minus norm of t minus y squared. Then there is this convergence factor. And then norm of c to the m over 2 u of y dt dy dc. So I have inserted a new integral, a t integral. Well, you see, when you integrate in t, this is what you are integrating. So you are integrating the Gaussian. And what you get is the integral will be basically this constant, this times some constant that's been absorbed here, okay? And so this is coming in to cancel out that, okay? This term. Okay, that clear? So now the reason I'm doing this is in order to be able to get the FBI transform in here. You see, the FBI transform, remember, has this thing. Okay. Okay, and so this then equals the same constant. Let me call it a constant depending on m. The limit as epsilon goes down to 0 of the FBI transform, and then ei x minus t dot c minus epsilon norm of c squared, c to the m over 2 dt dc. Let me explain this. The thing is, you see in here, you can write this part as I times x minus t dot c, and then pay back the t, but there is minus y dot c. So I write this like this. So this part is staying here. This part, e to the I t minus y dot c, and then together with this. And u is exactly what the FBI transform is, okay? And so that proves the theorem, the inversion formula, okay? So the way you use the inversion formula is, if you want to study some regularity properties of u, okay? Smoothness, real analyticity, Gevrey, or other regularities of u. If you are told a certain estimate on the FBI transform, some decay estimate of polynomial decay, or the reciprocal of polynomial decay at infinity, or exponential decay of some sort, if you are given a decay estimate on f, to deduce regularity of u, use this formula. And that's what we are going to see. Okay, we'll see today, hopefully. Okay? Any questions so far?
Which term was it that you added to ensure the convergence? You talked about the term that ensures the convergence of the integral.
What do you say?
You add the term into the integral.
You mean this term?
Yes, this one?
Yeah, this one. Yeah. You see, let us look at this. This is harmless, of course. The norm is 1. Let me look at this because I'm integrating over Rm cross Rm, right? So the t integral, if I look at f of tc in the t integral, if I look at the FBI transform, you see, in the x variable, because u is of compact support, when x is large, the FBI transform decays exponentially. So in the t variable, there is no problem. Okay. Now, in the C variable, there could be a problem, because for one thing I have this term, but this is exponential decay, so that's where this helps me, okay, in the C variable. Okay? But it won't matter eventually. Epsilon equals 0. All right.
Is this limit always going to exist?
Huh?
Is this limit always going to exist?
What, the limit?
Yes.
Not only does it exist, but it will require u of x. Part of the theorem is that not only does it exist, it equals u of x. Yeah. Okay? But to understand it really, what you need to do is go back to the Fourier inversion formula. Okay? The Fourier inversion formula is also saying exactly this, essentially. Okay? And if you understand the Fourier inversion formula, then it's just one more step. Okay?
If you using L infinity of R and then, if you using L infinity of R and then what can be?
If I take L infinity of?
You using L infinity.
Oh, if you use bounded.
Yeah.
Is that what you mean? Yeah?
Then
This will be true almost everywhere. If you use in LP, it will be true in the LP sense. If you use in LP log, it will be true. Yeah. Okay, these things have been studied, okay, by many people. Gives me a chance to advertise a book. There is a book by Berhanu, Cordaro. These are two colleagues in Brazil. Cordaro is a collaborator of Giuseppe on several research projects, and Huni. There is a book called Introduction to Involutive Structures. I hope to remember to send that to Florian. And in that there is a chapter on this, and all this is explained, okay? I'll also send some papers that Huni and I wrote over the years, where we studied, you know, what happens if you use in the Sobolev space, if you use in that space, this space, with applications to PDEs, okay? All right, so now let me come to real analyticity. So remember, I said the Fourier transform, the regular Fourier transform, is not good. It's not very good. It's not convenient, is what I should say. It's not very convenient to use in PDEs to study analyticity, to deduce that solutions of equations with real analytic coefficients are, say, analytic. Okay? I mean, solutions are not always analytic, but when they are, okay, the Fourier transform is not convenient. Because you have to take the Fourier transform of a sequence of functions. Okay? But first, let me remind you of real analyticity. What does real analytic mean? So real analyticity, I use this notation. So say U is real analytic at x naught means near x naught, okay? In Rm, if U equals a convergent power series, A alpha, a convergent power series centered at x naught, okay, for x in a neighborhood of x naught. So it equals this, okay? And the A alpha will then automatically be, they can be captured in terms of U, derivatives of U at x naught. Here the alpha is a multi-index, and alpha factorial by definition means the product of the factorials of the components. Okay? And sometimes I use the notation, the norm of alpha, which will mean alpha 1 plus alpha n. Okay? Okay, and yeah, the pen is not writing well. Should I try? Okay, thank you. Okay, well, this is even worse.
Okay, there is a new one here.
Yeah? Throw this away. Okay, thank you. Yeah, this is better. All right. So, so now, now the thing is that real analyticity is related to being holomorphic, to holomorphic. Okay. Then, if you are not familiar, if you are not comfortable with holomorphic functions of several variables, think of holomorphic functions of one variable. Okay. So see, holomorphic means I have to go to Cn. Okay. So if U is real analytic, this power series converges, right? This power series converges, say, in this ball, okay? In this ball. But then you see, I can write the following power series also. I can write this power series where this time z is in Cn, okay? And I take a ball in Cn now, center dot x naught of radius r. This also converges. I mean, when I take the norm, okay, it also converges. But the thing is that this then becomes, this is a holomorphic function. Okay, so this, let me call it maybe u tilde of z. Okay, so in one variable, you see, you had a real analytic function on this disk of radius r. And now I'm taking a holomorphic function in this ball of radius r. Okay? And let me call it u tilde of z. So u tilde of z is holomorphic in this disk. And it is an extension of the function u in real space. Okay, so this is how I can relate real analytic functions to holomorphic functions. Now I'm going to use this in a minute. Now, how do you check whether a function is real analytic or not? One way is that a function u is real analytic on an open set omega in Rm, if and only if, for all compact sets in omega, there is a constant depending on the compact set, such that the alpha's derivative of u at x on the compact set are controlled by this constant for all x in this compact set. Okay? If the alpha's derivatives are controlled by this, you see, if I insert for a alpha, this alpha's derivative divided by alpha factorial, then they're controlled by c to the power of alpha plus 1. So if x is close enough to x naught, the series will converge. Okay? Conversely, if u is real analytic, I just showed you, it means it's a restriction of holomorphic function, then you can use the Cauchy integral formula to prove this. Okay? Now, but the thing is, you see, in practice, this is not always easy to prove. Okay? So that's why this Fourier transform criteria become useful. Okay? This is not always easy to prove. You see, this is sometimes called Cauchy type estimate. The problem with this is that, of course, the alpha, if u is a smooth function, I mean, if it's a real analytic, it's in particular smooth. And so, of course, alpha derivatives on compact sets are bounded. But we are asking for a precise bound. The bound should look like this. And by the way, while I'm at it, Gevrey means u is in the Gevrey class GS, if and only if for each compact set, blah, 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 there is this such that the alpha derivative now grows like, it's almost like a real analyticity, but alpha factorial to the power of s. Okay, that's what Gevrey means. This you can define for s equal to, any number. Okay, s1 bigger. Okay, if s equals 1, it's exactly real analyticity. As s increases, these spaces become larger and larger. Okay. All right. So now, I said, because this is not convenient to work with, we need a Fourier transform criterion, and the FBI is going to do it. So let me remind you of what the FBI of a function is. It is the integral ei. I, by the way, I should have said is, well, it's square root of -1 minus norm of c, norm of x minus y squared, u of y dy. This is the FBI. So here is the theorem. Then I hope it's theorem 2 here. I don't want to mix up the numbering. Yeah, theorem 2. So theorem 2. So let u be a continuous function. I'm studying it near a point, so I just want it to be continuous near a point. But then I multiply by cutoff function and then say u is continuous on Rn. Okay. Then the following are equivalent. The following are equivalent. That u is real analytic at x naught When I say real analytic at x naught, I mean real analytic in the neighborhood of x naught, okay? And 2, that the FBI transform decays exponentially in the following sense. There exists a neighborhood v of x naught, a constant, I guess 2 constants, such that f of xc is less than or equal to constant e minus c2 norm of c for all x in V and C in Rm. Okay? You see, with a single transform, you can characterize analyticity. Single transform, okay? That's one of the nice things about it, okay? Now, we'll see, what did this introduce, remember, the nonlinear transform? As compared to the usual Fourier transform, it had this nonlinear part. You'll see where the nonlinear part comes in. Okay, you'll see where the nonlinear part comes in. The problem with the usual Fourier transform is the following. Notions like, regularity notions, smoothness, real analysis, say, for example, is a local notion. To check real analysis near x naught, I only have to look at u near x naught. But that's not what the Fourier transform does. The Fourier transform does not contain local information. When you look at the Fourier transform of u, it doesn't tell you what u is like near a particular point, right? This is related to the so-called uncertainty principle, blah, blah. But we'll see that with this nonlinear transform, you are going to get localized information, okay? Okay, that really is a big, the major insight of Brose and Iagolnitzer. Okay, so later this was expounded even more by Pfefferman, Charles Pfefferman. So I'm going to prove this theorem, okay? So that's the task today. Okay, one direction will be easier, shorter, namely 1 implies 2. Okay. But while I'm at it, let me also say, and in the references you'll be able to see the proof, that it also characterizes smoothness. U is smooth near x naught if and only if this guy decays polynomially, C1 over, just like the Paley winner, okay? And also Gevrey. Gevrey, U is in Gevrey class S if and only if the FBI decays like this, where here you have to the power of 1 over S, precise, okay? All right, so proof. So let's go this direction. Suppose U is real analytic at x naught, and I'm going to take a smooth function of compact support, which is 1 near x naught. I'll tell you exactly where I want it to be 1. So phi is 1 near x naught, and I want phi to be supported inside the set x naught where u is real analytic at x. Okay. Okay. So phi we understand. So it's a smooth function of compact support. It's 1 near x naught, then it becomes 0. Okay, that is phi. What I'm going to do is, so this is what I have to show. What I'm going to do is, well, u is real analytic. Remember, I said u is the restriction of holomorphic function. And so I have basically the integral of function which is a restriction of holomorphic function. Well, notice this is also a holomorphic function of y. And this also, you see, if you understand this as, forget the norm, think of it like this. You see, xj minus yj squared. Then this is also holomorphic in y. So to estimate this holomorphic integrand, you deform contour. I'm going to deform contour, okay? I'm going to deform contour. So here is how I deform it. Okay, so the first thing, what I just told you is that the integrand in the definition of the FBI transform is holomorphic in y for y near x naught. I mean, these guys are entire functions of y, but this guy is holomorphic only near x naught. Okay. Okay. So without loss of generality, I mean, I'm going to assume let u be the extension, the holomorphic extension of u. Instead of calling it u tilde, I call u, okay, extension. Okay. So you have x naught, and so in the neighborhood of x naught, in Cn now, in Cm, u is holomorphic. Okay. So deform contour as follows. So I'm going to go from Rm to its image inside Cm. I'll use the map theta of y. So this is going to be the new contour. And theta of y will be basically y away from x naught. So away from x naught, it will be the identity. But near x naught, I'm going to go inside here where u is holomorphic. That's where I can deform contour. Okay. Oh, let me write. Let me keep this. So I'll keep this. So I don't have to write it every time I want it. All right, so let me tell you what this contour is. So theta of y equals y minus I, then a small number s, which I will tell you what it is, and this unit vector. So I take c and 0. So for each c, I take this contour, but you'll see that the estimate I get will be independent of the c, okay? So let us see this. Phi is of compact support. So where phi is 0, it is y. So most of the time, theta of y is y. Theta of y is y over here. S is a small number, so this theta of y, it's different from y only near x naught. Okay, so this is some contour, something like this. So this is what the image of theta looks like. All right. So when I deform contour, then y gets replaced by theta of y, right? When you deform contour. Okay. Now, why can one deform contour? In complex analysis, why are you able to deform contour? It's because of Stokes' theorem. Now that's how I'm going to view it, because we are going to use that. We are going to deform contour also when I integrate things that are not holomorphic. Okay, I'll do that tomorrow maybe. Okay, or the day after. Okay, so just remember that deforming contour is really Stokes' theorem. Let me put it on a side here. You see what's deforming contour? So you take a domain. Say here is your domain. This is the boundary of the domain, and deforming contour means, so you are looking at, you see the integral of f of z, and then there is some form, but one of them is missing. Okay, blah blah. Let me. Maybe I'll be more specific in the future, but there is some form here. There is some form here. Let me call it omega form. Okay. So when you integrate this, Stokes' theorem tells you that this integral equals a double integral inside the integral of the differential, okay, of this. And then if this form already contains, say, dz1 wedge up to dzm in the z variables, this form contains this already, then when you take the differential, it's only the derivative with respect to zj bar that matter. And if f is holomorphic, those are 0. And so you get 0. So the integral of this thing over the boundary is 0, which means the integral over here is the same as the integral over here. That's what deforming contour means, okay? That's, okay, so here it leads to the following. So then after deforming contour, f of xc, fbi transform becomes the integral over Rm e to the power of, okay, so y is replaced by theta of y, as I said. So the whole thing, let me call it q of x, y, c. And at the bottom, y is theta of y. And dy is d theta of y, which means basically the determinant of the Jacobian of theta dy. Okay? The Jacobian of theta, you know, theta is changed only on a compact set. So the Jacobian of theta, you know, is is 0 most of the time. So it's only for y near x naught that matters. Okay? So this is controlled. There's no problem with this. It's a bounded thing. Okay? So to estimate this, then, I have to estimate this, which means I have to estimate the real part of Q. Okay? So that's the crux of the matter. I have to get, so if I write it out, the real part of Q explicitly equals the following. Minus S norm of C phi of y, 1 minus S phi of y, minus norm of C x minus y squared. Okay, so why do I get a decay? So now I said phi was 1 near x naught, so let me be more precise. So let phi of y be 1 when norm of y minus x naught is less than or equal to some delta. Okay? And then S, I didn't tell you what S is. The S, it has to be small enough so that in the image of theta, the image of theta lies inside the set where U is holomorphic. Okay, so if I choose S to be delta over 4, it will do. Okay, it will be good enough, delta over 4 or anything less. So let me now estimate the FBI transform. It's less than or equal to, I break up this integral into two parts. There is a part where y minus x naught is less than or equal to delta, and the part where y minus x naught is bigger than or equal to delta. All right, on this part, when y minus x naught is less than or equal to delta, you see phi is 1, okay? So if I look at just this part, I get e to the minus, and S is delta over 4 now, so e minus delta over 4, norm of C, 1 minus delta over 4. Okay, so maybe let me write it like this. 1 minus delta over 4 first, and then norm of C, and forget this. This is less than or equal to 0, so forget this. So this part, I call it, the first part, I call it I1 of xc. The second integral, let me call it I sub to integral 2 xc. All right, now, so let me look at I1. Let me estimate I1. It will be very easy to estimate I1. I1 xc. Well, when I estimate the FBI, there are also these terms, but these are bounded. Okay, these are bounded, so there is a constant c, there is a constant c. Okay. Okay, so this is what I'm estimating. So now this, you know, if delta is small, you know, say delta less than half, this will be less than certainly minus delta over say 8 or something like that. Okay. So I1 is easily seen to be less than or equal to a constant, the integral of e to the minus delta over 8 or delta over 16 times norm of C. This is a compact set. Okay, and these estimates are independent of the C. Okay, and so this part easily is less than or equal to some constant times e to the minus delta over 8 norm of C. Okay, very clear. Okay, so here, if you want, so when you choose your delta, choose delta to be less than 1/2, for example. Then you can even do better, but that's enough. And this is true for any x. There is no x here. For any x, this is true. So for all x, notice, this is true. X doesn't have to be near x naught. So the first integral is very simple. The second integral is not bad either. So in the second integral, what I do is, in the second integral, I forget this term. Remember, oh, maybe I never said that. I should have said that. Phi is non-negative, okay? Phi non-negative, phi less than or equal to 1. So because phi is non-negative, this expression, this whole expression is less than or equal to 0. So forget that. This is the one I focus on, okay? So this quadratic term is going to be useful here on this one. Okay, so u of y dy. This is what you don't get with the usual Fourier transform. Oh, it's not u of y, it's really this part. So there is that other part. Okay, but that other part is bounded by a constant. So let me focus on this one. So this one, you see, y is away from x naught. So if I choose x close enough to x naught, then I get E minus a constant times norm of c. Okay? So this time, unlike in here, this time x has to be restricted. Okay? So this time, so I2, so for x, for example, less than or equal to, say, anything less than delta. So delta over 2, the second integral, I2 xc is clearly less than or equal to some constant, e to the minus something like certainly something like delta over 8 times norm of c, or maybe delta over 16, but very easy to decide. Delta squared over 4 is what I have. That's fine. And so I have it. So the FBI, see, so the FBI was less than or equal to I1 plus I2, and both have exponential decay. Is that clear? For all x near x naught, but any c. Okay? All right, so now next we are going to go in the opposite direction. Okay? So this actually is typical in Fourier analysis. Whenever real analyticity arises in Fourier analysis, the different kinds of transforms, you expect them to decay exponentially, some form. Okay, so this is in keeping with that spirit. Okay, so next I'm going to go to the converse. I realize I only have 10 minutes left. There is no way I will be able to finish the proof, but I can start. So I will start, can finish it tomorrow. Okay. All right. So in the converse direction, so you are given that the FBI decays exponentially. So this is what you are given. So suppose this is less than or equal to C1 E minus C2 C. And this is for x in some neighborhood of x naught, and C in Rn. And you may assume, of course, that your point x naught is 0. Okay? So how, from decay of the transform, how are you going to deduce something about u, about analyticity? This is where the inversion formula comes in. You see, you have to be able to express u in terms of the inversion formula. So we call the inversion formula then. So, so you have u of x is the limit as epsilon goes to 0 of f of tc e I x minus t dot c minus epsilon norm of c squared norm of c to the m dt dc. Okay, so what we are going to do is the following. So I want to prove that u is real analytic near 0, which means I have to prove that u is the restriction of a holomorphic function near 0. Okay? So what I'm going to do is I'm going to break the region of integration into 4 regions And on each of the regions, what I will show is that these functions can be extended holomorphically to a uniform neighborhood, uniform independent of epsilon, and that the sequence as epsilon goes to 0 converges uniformly. And if a sequence of holomorphic functions converge uniformly, the limit is holomorphic, okay? And so I'll show that each of the integrals I get in the limit are holomorphic, okay? So this is a bit longer, okay? The proof, okay. So we will write this as a sum of, so basically as a limit of a sum of 4 integrals, ij epsilon, so for each epsilon, ij epsilon of x, j1 up to 4, where these ij's are as follows. So I1 epsilon, so I'm going to tell you the region in T space, where, so this will be the integral of this over that region. So this is the integral over the region TC where norm of T is less than or equal to A1 and C is in Rm. Okay, where A1 will be a number, a positive number. I'll tell you what it is in a moment. And I2 will be likewise the integral over the region where T is bigger than or equal to A2, A2 again to be specified. T is between A1 and A2, and C is less than or equal to B. This is to be specified. And I3 is the integral over a region in TC space where T is bigger than or equal to A2, no restriction on C. And now these 3 integrals, they will be very easy to analyze, very easy. It's the 4th integral that will require a little work. Not much, but a little work. I4 epsilon of x is the integral where T is less than or equal to A2 and C is bigger than or equal to B. The point is that the union of these 4 regions is Rm cross Rm, okay? So, as I said, I'll do this next time, but for now, let me mention the following, which will be relevant for the 4th integral. Is in the 4th integral, I'm going to deform contour in the C variable, okay? In the C variable. But you see, in the C variable, this is fine, it's holomorphic. This is C1 squared plus it. This is also entire. There is a problem with this, norm of C. So can you extend the norm of C? So in one variable, let's talk about in one variable. Okay, in one variable, if you have the function absolute value of x, okay, a function absolute value of x, right? Can you extend it? Where can you extend it as a holomorphic function? Okay. Away from 0, you can extend it. Okay. The way to see it is the following. The way to think of it is. Think of it as the square root of square. Now, if I take x plus iy, okay, square, the real part is this. I don't care about the imaginary parts. Okay. Now, when absolute x is bigger than absolute y, the real part is positive. Okay. Then I can take a holomorphic function log, an appropriate branch of log, namely a branch of log that is defined here, where the real part is positive. Okay? So log of then x plus I y squared. See, when absolute x is bigger than this, then this is positive, and therefore log of this makes sense. This is holomorphic. Okay? And so I want to define definition by this notation, I mean e to the half log of, so this is a holomorphic function. This function, this is a function, so is holomorphic for on x plus iy such that the real part in absolute value dominates the imaginary part in absolute value. The point is that this is a holomorphic function that extends this away from 0. At 0, it's not defined because there's no logarithm there, okay? So the thing is, this thing, where x is different from 0, but for any, and y equals 0, if y equals 0, I get exactly this, okay? And this works also in higher dimensions, okay? So in higher dimensions, so in Cn, so if you have this function, norm of C, so I do exactly the same thing. Define, let zeta be C plus I eta. So C and eta are in Rm now. And I take this, okay? I'm looking at this double cone, basically, okay? So you see, in one variable, this is where the extension is defined, okay, away from 0. And so in here, then I can take the same thing, you see. So I take zeta squared, which means zeta squared means it takes the components, zeta j squared, 1 up to m. If you look at the real part of this, what is the real part of that? It is norm of c squared minus norm of eta squared. And therefore, this will be positive, and so log of this, an appropriate branch of log, exists. So I define this function to be e to the half log of zeta squared. And this function, just as before, in real space, where c is different from 0, is exactly norm of c. Okay? It's a holomorphic extension. Okay? I use that to extend norm of c. Okay? And actually, did we have m over 2? Can you check? I thought we had m over 2. Not here. I don't think we had m. I think it was m over 2. I forget. I think it's m over 2.
Yes.
M over 2. Okay. Okay. So I need a holomorphic extension of that. But that's no problem. You see, the same things that I showed you. The square root means, you take logarithm. Okay? But I have a logarithm there. Okay? So I do have holomorphic extension of this in the c variable. This I'm going to use next time. Okay? I will not go over it again. Okay? Any question? Okay, another thing I'm going to do, just to give you a preview of, and I'll be done in 2 minutes. Another thing I'm going to do is I want to express a smooth function in terms of holomorphic functions in some sense. In some sense, in terms of holomorphic. Okay? Namely, the following. And this I will prove, and this will be very useful. A function u is infinity, say, on Rm. So let me call the variable x. If and only if there exists a C1 function, just C1, function of two variables. Let me call this maybe f this time. F of x is if and only if there is a C1 function of x and y on Cm, okay, so x plus iy is a variable, with the following property, that the restriction is f of x, and I said capital F is only C1. You can differentiate it only once, okay? And the derivative has the following property. If you look at d bar means what you do to check being holomorphic, right? If you look at the Cauchy-Riemann equations, this guy, well, when f is real analytic, then you have an extension, meaning this will be 0, right? But when f is infinity, what you get is that this guy should vanish to infinite order, meaning it should be like this for all k. Meaning, for any k, there is a constant c sub k such that this is bounded by c to the k to the power of that. Okay? This is a very nice characterization of smoothness. It's going to be very useful, we will see. Okay? The nice thing about it is you only need a C1 extension. Well, actually, I will show you that if f is infinity, there is a c infinity capital F that does this. But in the converse direction, if you have just a C1 extension with this, then f is infinity. this, what it will allow you to do is to deform contour when you deal with infinity objects, to deform contour almost like in complex analysis, because as I told you, deforming contour is really Stokes' theorem. And Stokes' theorem you can do for C1 functions, okay? So now let me explain the following. This is called vanishing to infinite order. When does a function have a property like this? If the function is infinity, it has a property like this if all its derivatives at y equal to 0 are 0. But if the function is only, well, in this case, this is only continuous, you cannot differentiate it. But however, you can still talk about this, vanishing to infinite order at y equal to 0, okay? So little f, this is how best you can do, how best you can compare it with holomorphic functions, okay? Remember, if this is 0, it is holomorphic. It's not 0, but near y equal to 0, where you have your data, capital F is behaving as if it is holomorphic, because it's trying to be as best approximating holomorphic functions, and I will stop here. Do you have any questions?
So can you please repeat the portion what was done? I was kind of lost.
Where? Here?
When you define yes.
Oh, the norm of x, absolute value of x. So basically, you see, the idea is, you see, absolute x is, after all, you know, I take x squared, I take half, okay? And so, and one way to write this is e to the half, at least when x is different from, like this. And I want to say, but this has the advantage that, you see, this could be holomorphic, you see. This part could be holomorphic, except you have to specify what log is, okay? And so if the real part of this is positive, say, for example, then logarithm is holomorphic there, and everything will work. Okay, so that's what I'm saying. Is that clear? Any other question? Yes?
We have a generalization of the Taylorian theorem.
What theorem?
Taylorian.
Taylor's theorem, you mean?
Yeah, Taylorian.
Taylor.
Taylor-Young.
Taylor-Young. For estimating the FBI transform?
For one function of one variable. If we
See.
we can locally write this from polynomial form.
I'm not sure I understand what you are saying. Sorry, I don't understand what you are saying.
Lorsqu'il écrivait la classe Gevrey, c'est comme une généralisation des développements limités pour des fonctions d'une seule variable.
Well, in French, I'm not sure.
I understand a little bit, but not, yeah, go ahead.
You can come, I can help if you need some translate. No? How about we do that? Since we're going to have a break, in any
Okay.
case, you can come closer and, okay?
Yeah.
Maybe we're going to think.
J'ai étudié la français il y a 40 ans. J'ai oublié. I studied only 40 years ago.